Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic, we're going to introduce the upcoming lectures where we will be approximating solutions to initial value problems. So in this topic, we will first review initial value problems, including first order, higher order, and systems of initial value problems. We will discuss the differences in the approaches we will use to finding, or in our case, approximating solutions to initial value problems. We'll introduce the concept of cubic splines to help us, and then we will describe the upcoming lectures. Now, an initial value problem can be written in, for example, the form where the first derivative is described in terms of the independent variable and the function. So, for example, here we have the first derivative is a function of t and y of t. We have an initial condition where the value of the function at t naught is y naught. Here's one such example. The derivative of the function is equal to t times the function plus t minus 1, and the initial condition is at time t equals 0, the value of the function is 1. Now, engineers generally describe the initial time as being 0. T naught is usually 0, as that's when we assume the system is being turned on, and we're seeing how the system progresses as time goes in the future. However, there may be certain circumstances where the initial time may be something other than 0. More generally, an initial value problem may be of the form of the nth derivative being described in terms of the independent variable, in this case t, the lower derivatives, and the function itself. Once again, note how we will describe the initial conditions in the abstract. T naught is the initial time, y naught is the initial value, y naught with superscript parenthesized 1 is the initial slope at time t naught, and for example, y naught superscript bracketed n minus 1 is the initial n minus first derivative at time t equals t naught. Here's one such example. Here we have the third derivative being the second derivative plus twice the product of the first derivative times the function itself plus sine of t. Here the initial time is t naught is equal to 1. The value of the function at t equals 1 is 2. The value of the slope at t equals 1 is 3. And the concavity at t equals 1 is 4. You can also have coupled initial value problems. Here we have a system of two initial value problems in two unknown functions, y1 and y2. And you can see that in each case, it's the derivative in terms of the other. Well, there's no lower derivatives here, but the function and the other function. And we have two initial conditions. At time t equals 0, the first function is 5,233. At time t equals 0, the second function is 323. Now, recall your approach in the calculus course for this particular initial value problem. In calculus, you find a single exact solution that is true for all time. So in your calculus course, you found that the y of t that satisfies both that differential equation and has the value of 1 at time t equals 0 is the function 2 times e to the negative t minus 1. What happens if you can't find an exact solution that is true for all time? Can we find an approximation that is true for all time? Well, we can't actually use such an approach. Instead, we're going to have a different approach. So what do we have from this initial value problem? Well, the initial condition tells us at time t equals 0, the value of the function is 1. But the first equation, the differential equation, says that if t is equal to 0 and the value of y at time t equals 0 is 1, then the derivative is negative 0 times 1 minus 1, which is negative 1. That says the initial slope is equal to negative 1. Now, from Taylor's series, you know that y at 0 plus h is the value of y at time t equals 0 plus h times the derivative at that time. And so in this case, that's equal to 1 plus negative 1 times h. Thus, if h is equal to 0.1, then we get that for this differential equation and initial condition, y at 0.1 is approximately equal to 0.9. Not exactly, but approximately. And you can determine that yourself by just looking at the solution. However, now we can proceed. If t is equal to 0.1 and the value of the function is 0.9, then we can calculate what the derivative should be. It should be slightly more than negative 1. It's actually negative 1.09. And if that is true, then y at 2 is y at 1 plus the slope at y at 1. And if we calculate that out, that's 0.9 minus 0.1 times negative, or plus 0.1 times negative 1.09, and that's equal to 0.791. All right, and then we can do that for time t equals 0.3, and then 0.4, and then 0.5, and so on and so forth. So in this course, we will approximate the solution at specific points, t0, t1, t2, t3, where each t value is greater than the previous. We are going to approximate the value of the solution with some value we find. That's the goal here. The only one we don't have to worry about is the first one, because the first one is given in the initial value problem. So that's given there. Now, with the differential equation and that initial value, we will estimate the value one time step into the future. Of course, there's going to be an error, but we can keep the error sufficiently small. At least we'll try to. With that point, we'll estimate the value of the function one further time step into the future. And we'll keep on doing this for as long as we need. And then we can approximate the function wherever we would like to do so. But we are going to do it one step at a time. We're going to use a number of different approaches to evaluate or estimate the value of the solution at various points t sub k. But suppose we want to approximate the solution at some point between two of these points that we've been given. So we want to approximate the value of the solution between, say, time tk minus 1 and time tk. What do? Do we just find the interpolating linear polynomial between 2 points? Well, a straight line isn't really differentiable, and then we'd be approximating a continuous and differentiable function with a piecewise linear function which is not differentiable at any of the points. Probably not. How about we take 4 points and we find an interpolating cubic polynomial between those 4 points. So if we wanted to find a value between tk minus 1 and tk, well, we can take the values at tk minus 2, tk minus 1, tk, and tk plus 1, find the interpolating cubic between these 4 points, and then evaluate that interpolating cubic at the point t that lies between the 2 inner points. That's another possibility. Let's actually implement this. Now, as before, we're going to shift and scale the solution so that we are at the points -1, 0, 1, and 2, and we're going to assume we are evaluating this interpolating polynomial at some point between 0 and 1. Now, for this to work, we have to assume that the difference between each of the tk values is equal. So the difference is some value h. Now we can figure out how far our point t is into that first subinterval. Hopefully, delta should be a value between 0 and 1. If delta is less than 0, then that means that t lies to the left of, in this case, the second point. And if it's greater than 1, it lies after the third point. We should only be using this technique to approximate the value of the function at points between, in this case, the second and the third point in these arrays. At that point, we can solve the above system of linear equations. We get the solution down there, and we use Horner's rule to evaluate it. And again, note that delta is a value between 0 and 1, so it will hopefully be reasonably small, and subtractive cancellation hopefully will not be an issue. However, let's introduce a different idea as opposed to interpolating polynomials. Recall that we have no control over the derivative of an interpolating polynomial, and yet we know exactly what the slope is at the two endpoints, at tk minus 1 and tk, because we already have estimates of the value of y at these 2 points, and therefore we can estimate the slopes based on the differential equation. We can find a cubic polynomial that satisfies these 4 conditions. First, the value of the polynomial is equal to yk minus 1 at the point tk minus 1, but also the derivative at that point matches the derivative given by the differential equation. Similarly, at the right-hand endpoint, the value of the polynomial matches the value that we estimate, and the slope at that point equals the slope as given by the ordinary differential equation. Now, this is the polynomial. It has 4 coefficients. We need 1 constraint for each coefficient, and we found that previously with 4 points, but now we have 2 points with 2 slopes. Well, we can differentiate that polynomial, and we can evaluate the derivative at tk minus 1 and tk, and that should equal the 2 slopes. Here's our matrix. It sort of looks a little bit like a van der Monde matrix, but again, it's slightly different. Notice immediately that we already know that a naught is yk minus 1, and the slope at that point is h times the value derivative, the value of the slope. Why h times? Because we are shifting and scaling so that the points are not tk minus 1 and tk, they're 0 and 1 to minimize error. However, that's the derivative at 0. Then we see the value of the function at 1 and the derivative at 1. That's actually a really simple matrix, so we can actually have some fun with that. Let's just eliminate the 2 entries below those first 2 entries. Let's just subtract equation 1 or row 1 from row 3, and we'll also subtract row 2 from row 3. So that gives us that system there. Now, at this point, we have that extra 2 there in location 4 too, so we'll add negative 2 times row 3 onto row 4, and that gives us that system there. We'll now subtract row 4 from row 3, and that gives us that system there. Now, it's a little bit awkward here because, well, that doesn't look like a normal system. However, what this tells you is, because there's only one per row and one per column, that A0 is the first entry, A1 is the second entry, A2 is the third entry, and A3 is that last entry. If you're just doing something back of the envelope calculation, this is more than sufficient. You don't have to be pristine. All right, so there's the solution, and let's implement this spline. Basically, a spline is a polynomial that has not only the value specified at 2 points, but also slopes and perhaps even concavities or higher derivatives. But in this case, we're only specifying the values and the slopes. 4 constraints, 4 coefficients. First, we're going to calculate h, because we will need it. We'll calculate the delta. How far is t into the interval from the first t value to the second t value? We'll assert that delta is between 0 and 1. And then we will simply apply Horner's rule for the polynomial we found. Notice again that delta is between 0 and 1, which is more or less what we're looking for. Now, which is better? A linear interpolating polynomial, a cubic polynomial interpolating 4 points, or a cubic spline? What we're going to do is we're going to take an initial value problem to which we already know the solution and find the following. First, we'll find the linear interpolating polynomial that goes between these 2 points. Then we'll find the cubic polynomial that interpolates these 4 points. Notice that the 2 endpoints are one time step into the past and the future, respectively. And then we'll find the cubic spline. And because it's an initial value problem, we also know the slopes at those 2 endpoints. We're then going to evaluate the actual solution and these approximations at a point between the 2 midpoints. 0.23 and change is between 0.2 and 0.25. First, here is an initial value problem to which you already know the solution. It's e to the negative t. That's the exact solution. If we interpolate the 2 points 0.2 and 0.25 with a linear interpolating polynomial and evaluate at that point 0.23 and change, we get this value here. That's the error. Well, that's not a very large error, but let's see how well an interpolating cubic does on 4 points. That's the estimation of the value at 0.23 and change, and the error has dropped significantly. However, if we calculate the spline and evaluate the spline at that point, we see that the error drops again by a factor of 10. All right, so this actually suggests cubic splines are the tool to use. Here's a different initial value problem. You probably don't know what the solution is to this one, but it happens to be this expression here. We can evaluate this solution at the point. We can find the linear interpolating polynomial and its error. Again, not very good. The cubic interpolating polynomial does much better with a much smaller error, and yet the spline does better. Again, the error drops by a factor of 10. We can also do this with any continuous and differentiable function. Let's suppose that we have the sine function, and we're going to first interpolate the sine function at 4 values, 0.2, 0.4, 0.6, 0.8, and we will see how close the interpolating polynomial is to the actual sine function. Well, that's the function below in red. And you can see that at 0.2, 0.4, 0.6, and 0.8, the error is 0 because, after all, it is an interpolating cubic that passes through those points. However, outside those points, the error grows rapidly. However, the blue function shows the error of the cubic spline that matches the values and derivatives at 0.4 and 0.6. As you can see, because the derivative is also matched, the error only starts to grow very slowly as you move away from 0.4 or 0.6. After all, that's what Taylor's series explicitly says. If you're matching the slope, then the error is going to be order h squared as you move away from it. And you do indeed see quadratic growth in that error at both 0.4 and 0.6 with the blue error. And between 0.4 and 0.6, the error is significantly smaller than the error of the interpolating cubic function. All right, so this strongly suggests that yes, indeed, using cubics is the preferred approach. The error of the spline is smaller by a factor of 10, so that's very desirable. Now we will begin and spend most of our time having and finding better and better techniques for approximating the solution to a first-order initial value problem. That is, where the ordinary differential equation is a first-order ordinary differential equation. That is one of the form where the derivative is equal to some expression in both the independent variable t and the value of the function y of t. What's really nice about this is that the techniques we find here can then be trivially generalized to allow us to, for example, find a solution or approximate a solution to a system of n coupled first-order initial value problems. For example, here we have an RLC circuit in this format, and if you were to write down the equations, you'd see the differential equations are the ones you see on the right-hand side. So we have two ordinary differential equations. What are the initial conditions? The initial conditions are, of course, the current on the inductor and the voltage between the two nodes that you see. Once we have that, we can actually use those techniques to approximate a solution to an nth order initial value problem. So, for example, this second order differential equation describes a pendulum. Notice on the right-hand side, we have sine of theta of t. So in this case, you need two initial conditions, which are, of course, the initial angle on the pendulum and the initial angular velocity of the pendulum. Here is an RLC circuit with a voltage source, which may be varying, and here we see that we have an expression in terms of the second derivative. And of course, now the initial conditions will be the charge on the capacitor and the current through the inductor. Following this, we'll see that it's even possible to use these same tools to solve a system of higher order coupled initial value problems. And that's actually what a lot of these circuit simulators do. These circuit simulators will do nothing more than take your schematic in VHDL, analyze it, convert it into initial value problems, and then approximate solutions to those initial value problems using the numerical tools we will see in this course. So, in this course, to approximate a solution to a first-order initial value problem, we will begin by looking at Euler's method. Then we'll see we can do slightly better with Hoyne's method. Now, following this, we are going to look at the classic fourth-order Runge-Kutta. Following this, we will introduce an adaptive Euler-Hoyne technique. This is interesting because it's going to then allow us to introduce a technique that is used quite commonly today, and that is the Dormant-Prince method. Finally, we're also going to introduce something called a stiff ODE and the backwards Euler method. But this will be for a special case. Now, once we have gone through these 6 approaches, we will then generalize all of these algorithms in such a way to approximate the solution to a system of first-order coupled initial value problems. And we'll see that this is actually quite trivial to do. It's as trivial, actually, as our generalization of Newton's method from Newton's method in one dimension, which is what you saw in your calculus course, to Newton's method in n dimensions, that is, using Newton's method to find a root of n nonlinear expressions. Then we will use this approach to approximate the solution to an nth order initial value problem, and then we should see that it's quite trivial to also be able to approximate the solution to a system of higher order initial value problems. So that will conclude this topic on approximating solutions to initial value problems. Following this topic, you now understand the various types of initial value problems we'll be looking at, and you have hopefully a better understanding of initial value problems. You are aware of the approach that we will use to find approximations to such problems. Whereas in calculus, you find a solution that is valid everywhere, here we will have to estimate a solution one point at a time, and then we will use cubic splines to estimate the value between such points. So you are now also aware of splines as opposed to interpolating polynomials. And you are aware in the next sequence of lectures we will be looking to approximate solutions to first order initial value problems, then to systems of first order initial value problems, which we can then use to convert a higher order initial value problem to a system of first order initial value problems, and then we'll trivially be able to just take general systems of higher order initial value problems and solve them as well. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!